Okay, thank you. Much anticipated welcome there. I'd ask you all to please stand for the King's Anthem. Thank you. I'd like to invite Dr. Davis, our head of school, to give a welcome. Dr. Davis.
So, good morning, everyone. Today is one of those rare, very special days at ISB when we have the privilege to listen to and indeed interact with a person who's contributed considerably to the progress of humankind. Kimberly will introduce Professor Schmidt in just a few moments, but before that I'll say a few words about the event itself. We're again honored to be part of the ASEAN Bridges series that the International Peace Foundation has hosted in Thailand, the Philippines, Malaysia, Cambodia, and more recently Vietnam since 2003. Participating Nobel laureates and other keynote speakers and artists have included Dr. Hans Blix, Jackie Chan, the Reverend Jesse Jackson, Vanessa May, Oliver Stone, Dam Amita Roderick, and Dr. James Wolfenson. And at ISB, we've played very proud hosts to Professor Harold Van Housen and Professor Romano Prodi. Now, the aim of Bridges is to facilitate and strengthen dialogue and communication between societies in Southeast Asia with their multiple cultures and faiths, as well as with people in other parts of the world, to promote understanding and trust. As an international school that's incredibly committed to global citizenship, we're honored to be hosting Professor Schmidt and to be part of the International Peace Foundation's work. With around 1 million students now studying in international schools across the world, the equivalent to a school system in a small country, international schools are the embodiment of the promotion of understanding and trust. Now, without any further ado, I'll turn you over to Kimberly, who will introduce our distinguished guest. Thank you.
I'd like to welcome and introduce the 2011 Nobel Laureate for Physics, Professor Bryan Schmidt. Professor Schmidt is a revolutionary astronomer from the Research School of Astronomy and Astrophysics at the Australian National University. He has multiple areas of focus concerning astronomy, but is best known for his research and discoveries of supernova, or exploding stars. In 1994, he and Nick Suntseff headed the High Z supernova search team, consisting of 20 astronomers from around the globe who studied distant exploding stars to piece together the story of the expansion of the universe back in time. Interestingly enough, the team found that the concept of an accelerating universe suggests that an unknown force is pushing the universe apart. In addition, Professor Schmidt is working on the study of gamma-ray bursts and is currently leading a project in the building of the Sky Mapper, a telescope that maps the southern sky. Please join me in welcoming Professor Schmidt.
Thank you, everyone. It is a great honor and a privilege to be here. One of the things that I love most about my job is being able to go out and talk to people around the world, not just about what I do, but about what you can do. And the reason that is that not that long ago, although it may seem like a long time ago to you, I was a student. I was at a school about this size in what many people in the world thought is a remote part of the world, Alaska, actually more remote than Bangkok. And I was studying science and studying math and history and English, and I had no idea what I was going to do with my life. And so presumably many of you are in that same position. Some of you may think you know what you're going to do with your life, but you don't really know, because that is the beautiful thing of the future, is it's very uncertain. So I think what I want to first concentrate on is the fact that the world works because people like yourselves get educated, they learn about the world, and we as humans learn to live in the world and manipulate it to make it better for us and hopefully better for other people and eventually better for other things. We're not very good at necessarily managing the world yet for the entire world, but I think that's coming over the next 100 years, or we will ourselves be in trouble. But you should realize that when we go through and we march forward as humanity, it is done by individuals. And we all think that when we look out and we see famous people, people who've won Nobel Prizes, people who've become president, we always think they're different than us. But they're not. They're people just like you that happen to be the right place at the right time, doing the right thing, and that's how humanity moves forward. It's not by super people. So when I look back to my time at high school, I had the opportunity to go back to my school a couple years ago and meet my teachers. And it was a great moment for me because I loved my teachers. They did a lot of things for me. But they were surprised that I won a Nobel Prize. Why would I, of all their students, win a Nobel Prize? I was a good student, but I wasn't like the best student. I was just another student. And as they said, they remembered me because they remembered that I was very good at organizing people to do things. And that turns out to be very important about science or anything. Is science and humanity moves forward not because of individuals taking their own steps, but it's about us walking forward together and trying to convince other people to help you, and you to help them is one of the most important skills that you can have as you go on with your studies. Because you need to learn what you don't know from people. You need to solve problems that you may not have to know the knowledge how to solve, and other people can help you do that. And it's by working collectively where we work together. I want you to think, and I'm going to show just a picture of a couple of pictures here. I want us to contemplate something. So this is a picture of the moon. This is something that even in Bangkok you can see. And now what I'm going to do is I'm going to take a $2 billion spacecraft known as the Hubble Space Telescope. And we're going to stare at this piece of sky, and we're going to stare at it for a couple months. A tiny little piece of sky, about that big. That turns out to be 1/13 millionth of the entire sky. So I have to take 13 million pictures like this, but then I've taken a picture of the entire sky. And what do I see when I do that? This is what I see. I see a picture of the universe, a picture full of 20,000 galaxies, each galaxy not dissimilar to the galaxy we live in, the Milky Way. Each of these galaxies has 100 billion stars like our own sun in it. And what we know now from other telescope observations is about 1 in 5 of those stars will have a habitable planet like the Earth around it. we can go through and we can count up and say, well, how many habitable planets are there in the visible universe? And the answer is a number so large that, it has like 26 or 27 zeros behind it. That's more grains, that's more than the number of grains of sand on planet Earth. That's how many habitable planets. And we here on Earth, tiny little drop in the ocean, have been able, by working together over the last several thousand years, piece together our place in the universe. Think how profound that is. That we are insignificant, yet by using the fact that we learn from each other, that every smart thought that humanity has had over the last several hundred years has been shared with every other human. It's the fact that we are able to do that that allows us to move forward. When we make a discovery in science, we don't keep it to ourselves. We share it with everyone so that everyone in the world can then use that piece of information to make their own discoveries and build upon that. And that's one of the beautiful things about science, and it's one of the things that this series, the Bridges series that I'm part of, is trying to remind people of. Because sometimes we forget it. But it is at the very core of humanity and what makes humanity good and what makes life good. We should remember that. So one of the questions you might ask yourself is, why did we spend $2 billion to go through and take that picture? $2 billion. Well, it's because it's a very interesting picture. It allows us to think about our place in the universe. That's probably why we didn't spend $2 billion. That's why we did it. But in making that picture, think of all the technology we've had to do. We've had to develop advanced digital cameras. The digital cameras that we all have on our phones now. Right? That's a billion-dollar, multi-billion-dollar industry. In this phone, I have Wi-Fi. Wi-Fi was invented by one of my Australian colleagues, a radio astronomer, who was looking for Stephen Hawking's black holes that evaporate, and he never found them. But he became a very, very rich man by using the technology which failed him in science to develop Australia's most valuable invention. If we look at the components of this phone, they all are made up of Nobel Prizes in physics that apparently had no use when they were made. And yet they all come together. That knowledge being pieced together is incredibly valuable, even if in its own individual part it's not. So people like to come, for example, my science minister. Why do we care that the universe is accelerating? The discovery I made, the fact that when we look at the universe is going further and further away from us in all directions. And more interestingly, when we look to further and further distances, we're looking back in time. And we can do that same measurement of how fast is the universe moving away from us in all directions, and how fast is it now compared to the past. And it turns out in the past, the measurement I was able to make was that the universe was expanding slower in the past and had sped up. Well, that was a surprise. What would cause the universe to speed up? That's like throwing a rock up in the air and have it speed away from me rather than be slowed down by gravity and come back down to Earth. So that was the discovery I made, and it infers the idea that space itself is made out of energy, and that 70% of the entire universe is this energy, part of space. And it turns out, under Einstein's theory of general relativity, this energy makes gravity push rather than pull. So I have no idea what use this is going to be. It's probably not going to make anti-gravity machines in the near future. but it's a fundamental piece of our universe. It's 70% of our universe. And so it's important. We just don't know if it's going to be important in some way in the future or not. Every piece of information is important. So people your age often ask me, what do I have to do to win a Nobel Prize? And the answer is, when I was your age, I didn't think about winning Nobel Prizes. I didn't even think I'd be able to be an astronomer. I was happy just being able to explore the universe. And that's exactly what wins people Nobel Prizes, by going out and doing good work and then suddenly coming across something unexpected in their work. Nobel Prizes are won by people like yourselves. Now, I can't guarantee that any person in this room is going to win a Nobel Prize, but I'd also say you're as likely as anyone else I have ever met to win one. And that's the way society moves forward, is again working together, making those discoveries, some of us, and then sharing them. And it doesn't matter if you win a Nobel Prize or you don't, because I can tell you the most exciting thing in my life was not winning the Nobel Prize. It was actually doing the work that led to the discovery. The discovery itself was kind of terrifying, because I thought it must be wrong. This is crazy. I've discovered that 70% of the universe is anti-gravity. That's not something that you put on your homework and you expect to get full marks when you get your homework back. So the excitement is actually just doing the work, going out and exploring. And it doesn't matter if you're a scientist or you're an economist like my wife is, a politician, God forbid, or anything in between. It's the journey that's exciting. And I'll stop there, and this is all about having a dialogue, so I'm hoping we're going to have a chance to ask and answer many questions, but I want to indicate that there is no such thing as a dumb question. Unless it's so smart I can't answer it, then it's a dumb question. Hi.
Hey. Can you hear me? Yeah.
I can, but feel free to stoop over a little bit to get close to the mic.
All right, so in the past...
Tell us your name first.
Oh, sorry.
I don't know who you are. I think everyone else does.
My name's Austin.
Okay, nice to meet you.
Hi. Nice to meet you too. So in the past 25 years, many new inventions have been created for the purpose of learning more about the universe. For example, the Hubble telescope you mentioned.
Yep.
Have these inventions enabled or accelerated the discovery of new knowledge?
So it turns out that science is completely built in a virtuous cycle around technology. So in my case, there was technology that allowed me to make my discovery were these big digital cameras. Why were the digital cameras being made bigger? Because astronomers needed them to be bigger. And so we were pushing on how to make larger and larger digital cameras so we could survey the sky faster and faster. Eventually they became so big they became useful as digital cameras for all of you and all of me. You know, I use a digital camera too. And it turns out that once they got that big, industry could take over and mass produce them. Telescopes. The other thing we needed was telescopes. The little 4-meter in diameter telescopes, which cost you about $20 or $30 million, they weren't big enough. We needed 10-meter telescopes. So telescopes getting close to the size of this stage. And so those came online in 1994. The large digital cameras came in line in 1994. And then finally we needed computers to sift through all that data, because we would take, 50 gigabytes of data at a time, which doesn't sound like much now, but back in 1994, just to remember that a 50 gigabytes of data is about a full Blu-ray, right? A 2.5-hour Blu-ray movie. And what we had to do is find a little speck somewhere in that movie, and we had to find it really quick. Not a big speck, just a little tiny one you could barely see. So we had to develop computer technology. The computers had to be powerful enough to process that data. So that technology is really important. But in doing the science, we of course develop the technology. So it feeds back in. We help develop technology, it gets mainstream so we all can use it, which makes it cheap and easy for us to use, allowing us to develop new things on the cutting edge. And so that is integral to my discovery, but to every piece of science, right? When you go in and you do medical research, they use magnetic resonance imaging all the time now. And that's a Nobel Prize from 30 or 40 years ago. And that allows them to do that work even more and more detailed. And so it's a beautiful cycle of technology allowing you to do new things, allowing you to develop new technology, which then feeds back in a beautiful circle. Yep. Thank you.
Thank you.
Yep.
Hello, I'm Anthony.
Hi, Anthony.
As science recently has driven, in the past few hundred years, has driven philosophical arguments such as John Locke that was partly due to the scientific revolution, do you think it would be a good idea for governments to use science and or pragmatism as a key decision-making tool in government/politics?
So it is absolutely critical for what we call evidence-based policy. That is, you have evidence and you make policies using that evidence. But not everything probably boils down to evidence. Some of it boils down to ethics and morality. So for example, and this comes into as I said, economics, and my wife, being an economist, has to deal with this question all the time. Imagine the government has money to spend to do science education. What's the outcome we want? We can look at evidence, and now we can concentrate the money for science education in a few schools so that a few people become really, really, really educated. Or we can spread the money more thinly to make sure that everyone gets a certain level of education. It may well be that concentrating the education gives you more money into the economy, but it may be that having a bunch of uneducated people leads to other problems, like social unrest. And so at some point you have to make a call based on something other than just evidence. That being said, the sad part about many policy decisions around the world is they don't bother about the evidence at all. And they make a choice not along that curve of what's the best way to spend the money, deciding between concentration and spreading. They just do something random because they haven't looked at evidence at all. So it's really important, I think, if we're going to spend money and have governments work well, is to base things on evidence. But to always know there's always going to be a political decision about exactly what to do in most cases. Climate change, the same thing. When I deal with my own country, where there seems to be a fair bit of skepticism about the scientific evidence towards climate change, when I talk to the politicians who are skeptical, they do not understand the scientific evidence, period. This is the only area in science where they suddenly have an opinion. I have no idea why. It befuddles me. That being said, once I can convince them that actually adding large amounts of carbon dioxide to the atmosphere does affect the climate, that does not prescribe what the correct response is. I think we need to do something because things are going to change in ways that are going to cause lots of damage in the future. But exactly what the response should be, that ends up being an economic and a political decision, again. So you need to use evidence, but we as scientists also need to respect the fact that there is something else beyond just the hard facts in making many decisions about how we run the world around us. Okay? Thank you.
Thank you.
Hi.
Hi.
I'm Abby.
Hi, Abby.
What's the best advice you can give a student interested in studying astrophysics or astrology?
So, astronomy, be careful.
Astronomy.
Never,
Sorry.
ever, ever say astrology. Yes. Best advice. So, the best advice I can tell you is that when you have a chance to study something, when you're young, don't do what other people think you should do. Do what you think you should do. Okay? You're too young to start having to make compromises about what you want to do in life. The advantage of studying something like astrophysics or something, it doesn't matter if it's astrophysics or, medicine or whatever. If you love what you're doing, if you're really interested in it, you will do it well. And if you learn something you're interested in, you learn it well. If you try to study something you're not very interested in, it's a chore, and try to do that for 4 years and you don't do it very well. And so when you're 17 or 18 or 16, it's really important, I think, when you try to choose your studies, to realize that doing something that interests you has huge advantages. Now, the world can only support so many astrophysicists. We don't need 10 million of them, it turns out. That being said, when we look at people trained in astrophysics, they have skills of computing, of physics, of engineering, of math, that are very useful to do almost anything you can imagine. So the skill set you get in studying something is also useful. I would always argue that when I train someone in astronomy, I'm actually training them to think and to have a tool set that can be used for anything. Because I know that probably 9 out of 10 people who I train in astronomy are going to do something other than astronomy in the rest of their life. But the good news is the unemployment rate is very, very low. It's among the lowest of any discipline you can study, about 1%. Okay? So it doesn't mean I can guarantee everyone a job, and if everyone decides to become an astrophysicist, then we're going to have some problems. But you need to also realize that you need to have the skill sets. So in astronomy, you need to be good at math. You got to really quite like calculus. It's got to be fun, because you're going to use a lot of it. Physics has to be something. That's at the core of astrophysics. So physics is something that you have to enjoy. And you have to enjoy the idea of going out and doing research. Research is not about following a recipe. Research is thinking about a question, saying, how do I use my skill set to answer this question that no one has ever answered before? And that's quite a different skill. So keep an open mind. Sometimes life does throw things at you where you have to make a decision. But that is, you can't do exactly what you want. But when you're 17, trying to decide what you want to do, this is probably not the time to start making compromises. And some people are very worried about saying, well, if there's only a 1 in 10 chance that I'm going to become an astrophysicist, why am I going to study astrophysics? And the answer I give is the following. When I started studying astrophysics, I did not think I was going to ever become an astronomer. I knew the odds, and I said, not going to happen to me. But I knew I'd be able to get a job. And I knew there was some chance I'd be able to become an astronomer. But I also knew that there was a very good chance I wouldn't. But what was my alternative? My alternative was to go and study something I didn't like as well as astronomy, have no chance of ever doing something I was really interested in, and just drill that into the future. And the reality is that once I got my astronomy degree, I was just as capable of doing these other jobs as I was without it, because it's a very useful degree. Okay? So I would argue that most of you should follow your heart at this point of your career. At some point you will have to make a hard decision. But if you love something, then I can only provide you encouragement to study it, and study it until you have to make a decision not to study it, because that will leave you in better stead for the future. Why? Because imagine you study something now. What's useful now? Well, you're 17. You're going to still be working 45 or 50 years from now. What's going to be useful 50 years from now? You have no idea. You want to have something, the ideas of how to think and to adapt and to have skills that you can transfer onto other things. That is your way to future-proof your life, not going through and working something very specific for the moment. Thank you.
Thank you.
Hi, I'm Leo. I'm presenting this question on behalf of a classmate, Namvu.
Okay.
Yeah. He says, do you think it would be valuable to alter the content of high school science classes to include more on the historical context of science and or teaching about historical failures in science?
Ah, interesting. So, absolutely yes. So I am a big believer in the history of science, and indeed when you take my third-year cosmology class, which has got lots of tensors and other things which you probably haven't learned yet in it, very mathematical, I spend a fair bit of time talking precisely about the history of science, how it was done, the mistakes made, the rabbit holes that the field went down, so that people get a sense of how science works. Because from my experience, the way we are taught science is very different from how science actually occurs. It is very rare that we sit down and we say, here is my hypothesis written out as a two-sentence thing, and here is my test. If you restrict yourself as a scientist to that, progress is too slow. Okay? So you will have a hypothesis, and you will test it, and you will test lots and lots and lots of hypotheses. And one of the issues is how you get that information out, and it's one of the problems for science. But you tend to sift through lots of information quickly to find the things that are interesting. That's just the way science works, and that's not the way it's taught. But if you go through and you look at the way science is developed, you will see that that notion of a hypothesis is not how things went. If you look at DNA, how DNA was figured out, that was people going through lots and lots and lots of ideas very quickly. And yes, it was a hypothesis, but they weren't written down as that. It was written down as this process. And so I think it's really important to see how things are done. It's a very important part of science, is the history. Because ultimately science is done by humans. And we make mistakes, we have prejudices. It's not black and white. And that's a really important concept about science, is we're often taught that things are right or wrong. Well, nothing is right or wrong in science. You have evidence that at a higher and higher degree of confidence rules out ideas. But nothing is ever absolutely wrong. And that is at the heart of science. And when you study the history of science, you can see how that evolves over time, and how mistakes are made, and how science corrects those mistakes. And by doing that, you can understand, for example, I think, some of the things that are going on in the climate change discussion right now. Although the climate change discussion is rather unique in that it's really the first time that large fractions of the world who are not scientists suddenly have a very strong view of what the scientific answer is. And it's almost religious in that respect, of how evolution crosses over into religion in a very simple way, similar way. Thank you.
Hi, I'm Esther. Finding out that the universe is expanding probably evoked many other questions as well. Have you been researching any new ideas or questions formed from your recent discovery? If so, what is it? If not, what are you currently working on?
Okay, so the universe is speeding up. We think space is full of energy. Now, it turns out every cubic meter of space, so something here, contains a tiny, tiny amount of this dark energy. It's very hard to study. The entire Earth contains a microgram of dark energy, a microgram. So if you want to do an experiment here on Earth to figure out what dark energy is, no one's figured out a way to do it. So what's dark energy? We don't really know. We know it's there, but we don't know why it's there. Our best theory comes from quantum field theory, quantum mechanics, and the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle within quantum mechanics says that particles can come in and out of existence for a very, very short period of time. Pretty much, in one word, anything's possible given a short enough period of time. And so we expect from this theory, which seems to have been able to predict the Higgs boson and everything in between, that particles in this room should be coming in and out of existence for a tiny fraction of a second, 10 to the minus 25 seconds. And when you go through and you say, well, let's just add up how many times that's happening in a box, that's a cubic meter, it turns out it should be happening so much that the energy equivalent in a box in this room should be about the weight of the entire universe. The weight of the entire universe in this box. So that is the prediction of our best tested physical theory. So it's wrong. And it's wrong by 120 orders of magnitude. That is, that answer you get, you have to multiply by decimal place 120 zeros and a 1 to get the answer of what I've measured. So we have a problem. We have a theory that predicts dark energy should exist. It just gets the wrong answer by the largest mistake in any part of science ever. Okay? So solving that mystery is a big problem. We don't know why it's there. So that's one of the things I'm working on, is to try to figure out and to measure exactly how this dark energy behaves and to see if it fits one of the theories. And at this point, we're scratching our head. Our best theory is that from Albert Einstein in 1917. But even that theory, we don't know why the dark energy should be there. It's just that it is there. So that's one of the things I'm looking at. Completely different types of things I'm looking at. I'm looking for the planets. You know, all those planets I told you around each star? Well, sometimes they're lined up so that they go directly between the star and Earth. And so you get what we call a transit. This is something Venus did in 2012 and won't do again till another 108 years. And when it does that, that star is going to be a certain brightness. It's going to go a little dimmer and a little brighter. And we can discover planets this way. So I'm part of a team that's looking for planets. Why do I want to find planets like this? Because when they go in front of their stars, that star's light shines through their atmosphere. And when light shines through its atmosphere, it picks up the spectral fingerprints, the colors, the light has little fingerprints of light, of color, which identify what's in that atmosphere. So imagine that a distant civilization was looking at Earth when Earth went in front of the sun. What would it see? It would see oxygen, and it would see lots of oxygen. But if you do the chemistry, there shouldn't be oxygen on planet Earth, except for if there's life. The reason there's all this oxygen on Earth is because of life. You might also see interesting things like CFCs, things that get rid of ozone, we're gradually getting rid of. They have a very specific signature as well. So that would be a way to figure out if a civilization had created chemicals and polluted their atmosphere like we have. So it is a way that we can identify life in the future, and we are probably going to be able to start doing this in the next 10 or 15 years when the next generation of telescopes come. The final thing I work on is when we look back to this era, we're looking back about 12.5 billion years. I like to look just a little bit further to the era where there are no stars and no galaxies yet, because they haven't been formed yet after the Big Bang. So it's quite amazing. That picture, if I make a bigger telescope, I don't see more stars and galaxies because they don't exist. They haven't formed yet. And I can only look back 13.8 billion years because the universe just didn't exist. So I can't see any further than that. So the universe is huge. It's probably even infinite or close to being infinite. But the part I can see is finite because I can only see a sphere around us, 13.8 billion years. But how did the stars and galaxies come to existence? Well, that's an interesting question. We know gravity took what was left over from the Big Bang and collapsed it down to make stars and galaxies. But that's really all we know. But with the next generation of telescopes, both in radio, something we're building in Australia, a big radio array to look at the hydrogen back at these times, but I also look at exploding stars, the brightest things in the universe, called gamma ray bursts, and they flare up for a few seconds, shine through the universe, and I can actually see what the universe is made up of back there, and I can start seeing how all the chemical elements were formed. And then in our own Milky Way, I look at each star with the new telescope called Sky Mapper that you heard in the introduction, and I can see what each star is made out of. And it turns out earlier this year, or actually last year in 2014, we discovered the first star that has no iron in it at all. Why is that important? Because the Big Bang made hydrogen and helium, and that's it. And we discovered a star that had no iron, because the iron is made in the stars after the Big Bang. So this star, it turns out, is one of the earliest fossils of the universe. And we found one of them, but we want to find hundreds of them so we can figure out how those first stars were formed. So that's what I'm working on. Thank you.
Hi, I'm Kolhat.
Hi, nice to see you.
So a lot of times astronomers are studying things that are so remote to our lives. And so why would any of the knowledge that we are seeking in science that's so far away from our life matter to us?
So I tried to give you indication of why what we do matters. Partially the reason we do astronomy, hopefully, is because it's interesting. When we look back to the earliest times, the common stories that all of the cultures have in the world are the stars. That's the thing we've shared. Every culture has shared. So when I go and I meet especially 10-year-olds that are not jaded yet by science classes, they all like to understand what's going on. They're like, oh, cool, how's this work? And it doesn't matter when I go to Namibia or if I go to Australia or I come to Thailand, they get it. This is interesting. It's part of what we are. But in terms of the benefits to society, in the process of learning that, I train people to think, to solve problems. So most of the people I train do things other than astronomy. They go through and they solve hard problems. One of my students tries to figure out how to manage risks so that if a natural disaster happens in Australia, we can deploy resources to make sure no one gets hurt or as few people get hurt and everything works well. But why would astronomy do that? Well, it turns out that's an optimization problem. It's how you go through and you spend your money wisely. And we solve those types of problems all the time in astronomy. The math and the statistics and the physics and the computation all compare to that. Another one of my students is using machine learning to go through people's credit card records and to sell them products that they want better. So that when you go on your phone the next time and it pops up and says, PlayStation 4, it's figured out you want a PlayStation 4, right? And so that helps other people make money, but it's useful for you as well. It's not all bad, because it means you're not wasting your time, getting bikini advertisements that don't have a lot of use for you, right? You get something you're interested in. Give yourself a couple years, maybe it'll be useful. But anyway, the point being is the people who work with, I should say, a couple other people I'm working on are using the techniques that we use to discover the exploding stars, that we use to discover the accelerating universe. They're using those techniques to look for patterns in people's DNA to help cure cancer. And they're developing the instruments that we use to look at the stars to help image people's bodies so they can look for breast cancer more quickly. It goes on and on and on. It's the knowledge, it's transferable. And the cool thing is a lot of people like to learn about the stars, and they're willing to learn, you know, very complicated mathematics, very complicated statistics, very complicated physics in a way that they might not be willing to do if I just said, all right, Michelin needs to hire you. Why don't you go out and bust your butt for the next 4 years so that you can get a good job? That abstract way turns out not to motivate people to learn very well. And as I said, along the way, you learn all these things that can be transferred. Wi-Fi, the internet. CERN cost 8 billion euros. 8 billion euros we spent. That's a lot of baht. Okay? So why did we do that? Well, because it's interesting. But in the process, we invented the web, the World Wide Web. That's $1 trillion, trillion euros a year. Pretty good investment. So that's why we do it. Thank you.
Thank you.
Hi, my name is Jessie.
Yep.
And I know that you first started off your work with the expansion of the universe, expecting to find evidence for the deceleration of the universe, but in turn you discovered evidence to show that expansion rate is accelerating. As a scientist, how do you deal with the discrepancies between what you expected and what you actually find?
So as a scientist, I'm just a human. And so, as I indicated, when we went out at the end of 1997 and we started looking at our data, and we were getting the wrong answer. The universe was supposed to be slowing down, and the question is, would it slow down a little bit and keep on going forever? Or would it slow down a lot, stop, and go into reverse and have what I like to call the Gnab-Gib, which is the Big Bang backwards? So that was what we were trying to do. So we go through, we do our measurement, and the universe isn't slowing down at all, it's speeding up. So we've got the wrong answer. So at some point, the first thing I did is said, wow, we've got the wrong answer. And I didn't go, eureka. I said, okay, let's go back through every part of the experiment and find our mistake. So we did that. We went through the whole experiment and looked for the mistake. And we didn't find the mistake. Then we're scratching our head saying, okay, pretty sure we haven't made a mistake. Guess we're going to have to tell everyone. I don't think people are going to believe us. There's always in the word of Donald Rumsfeld, who I never thought I would think was a genius, but I'm convinced is a genius now, something in the form of what he called the unknown unknowns. So we had gone through and looked at what we call the known unknowns, the things that we're worried about that could be wrong, and we had checked them all, and they were all okay. But there's always the thing that you didn't think about. So that's what I was worried about, the unknown unknowns. And so when we published our finding, I was pretty sure that the only thing that was going to get us was something that not only we had not thought of, but no one had thought of. And so I was worried. And if it came out a week later, it's going to be embarrassing. After a year, I was like, okay, we're okay now, because even if it goes away, it's not really our fault. Everyone collectively makes a mistake. And then at some point in 2000, another experiment came along, and was a very different experiment than ours, and it verified our result. And I remember waking up that day, reading that paper on the internet, and I was like, I'll be damned, we're right. But I wasn't sure until that moment, right? So there's doubt. But it's okay. One of the things that we don't teach well in school is it's all right to be wrong occasionally, to make mistakes. And indeed, if you never make mistakes, then you're not taking any risks. You need to be willing to, you got to do a good job. Making mistakes is not the goal. But if you don't take some risks, you're not going to ever make mistakes. But the key is figuring out your mistakes yourself, not letting other people point them out to you. Find them quickly and then move on. So you got to be willing to take the risk of trying something, of it not quite panning out as you expect, and moving on. And that's why, you know, when we're talking about what to study, if you really, really want to go study something, try it out. But if it's not quite what you thought, and you're like, oh, you know, I actually don't like this, then do something else and be willing to move on. with your life quite quickly. And that's how scientists, and that's why I say the scientific process is a little different. It's really going and failing on things. You try something that doesn't work, try something out, try something, and then suddenly, oh, this works. And so that's the way science works, is you try things, you fail, you move on. So I visited Google for the first time about 1.5 years ago, and their motto is fail often, fail quickly. And that's a good motto for success. It's worked for them, at least. Thank you.
Thank you.
Hi, I'm Nikita. How does an astronomer decide if an object seen through a telescope is something that hasn't been seen before?
Well, the good news is thanks to the World Wide Web, every image that we take now is on the web. And so we go through, and if, for example, I make a discovery. So right now, I have a telescope in Australia that is mapping out about 1,000 moons worth of sky every night to about 1 million times fainter you can see with the human eye. And we are comparing to past images. So we digitally take that data, and now we're doing about 1 terabyte a night, so it's a lot of data. And we digitally subtract it, and we look, and we say, was it there, was it not? And so we're actually using a reference, so, you know, sort of a reference library of images. And then if we find something, we'll post it to all the other astronomers. And astronomers will check their records, and they'll either say, oh, that's new, never seen anything there before, or they'll say, oh, you know, actually, we saw something back in 2011 there. Maybe it's not an exploding star, maybe it's a variable star in our own Milky Way. Boring, okay? We call those the cockroaches of the night sky. But the beautiful thing of science is we share our information. So I can literally look up every object on the internet now, every position in the sky, down to something, you know, literally a 10,000th of a degree in both directions, and I can say what's there, what's been there for the last 100 years. And I can see if there's something new or if there's something interesting. So for example, the star that we discovered, that first star with no iron, it's a bright star. You could see it with a telescope here at this school if you had just an amateur telescope. But you wouldn't know it was interesting. And what we were able to do is to sift through the 100 million stars in the sky that are like this one and say, that one's interesting. And we knew by looking through the records that no one had ever found it before. Because normally when you find something interesting in science, you want to tell people around the world about it. That's the way science works. That's how you become famous. You don't gain any fame by holding on to your discoveries and not telling everyone. Because science is very unkind to people who said, oh, I could have told you about that a couple years ago, but I decided not to. That turns out they just either call you a liar or a fool if you do that. So, thank you. All right.
Thank you, Professor Schmidt, for such an insightful speech. As students who are looking to figure out what we want to do in the future, it is an honor to have someone who has already achieved so much come speak to us. We really appreciate your time and knowledge. We would like to now honor you with a small token of appreciation. Could the people who asked questions come on stage to take a photo with Professor Bryan Schmidt?
It's been taken. I'd ask the students to remain seated, please, while faculty leave first. Thank you very much. Thank you.